Hello world and welcome to Code or Not to Code. I'm Millie Eva and as always I'm very happy to be here today and I'm here with Stefan. How are you doing?
I'm doing great. It's April's Fool's episode and there has been don't want to say the company, but there has been a major source code leak and I'm still not convinced if this is an accident or some fool's joke, but who knows?
Yeah, you have
who
to
knows?
be so careful today. I stayed away from quite a few of social media or like media in general because I was terrified. I didn't even read all the messages at work. But yeah, no, it is April Fool's. Sorry?
Oh yeah. These days it seems that every news entry could be a fool's. A premature or delayed fools these days, but that's a different story.
I wish sometimes, like, I wish it was just a joke, but it's not. It's real life. Wonderful, isn't it fun to live in 2026? Especially if you get to be here with us today. Yes, if you're new to the show, Stefan and I do meet every other week and code together. We've done this for a couple of years because we just can't get enough of each other. We used to work together. Now that we don't, well, we have to find other ways to explore some code together. And it's always, we always learn something. We always have fun. And we've done the April Fool's episode for a couple of years now. And I'm really, really glad that we sort of do it like bang on the 1st of April. Almost, I think, was it every year? Did we ever do it not exactly on April 1st?
I'm not sure, actually.
But if you would like to find out, you just have to go on our YouTube channel and see. Yeah, we did.
Actually, we didn't school further. That's been more than two years ago.
Wow,
no, we didn't. We actually didn't. No, actually, I think this is our second episode.
Is it?
Yeah, I thought we had more as well.
That's disgusting. Well, it won't be our last. And I think maybe we just did like fun episodes every year, like where we don't really work on the projects we're supposed to, but we just explore some fun things. I think last year we did it because we actually did it in preparation of a talk that we did.
Yes, indeed, yeah.
Where we had some shenanigans that you can do with C#, where you can set each other up for failure. So usually we try and set each other up for success, and every now and again we try and do the opposite, especially on April Fool's Day. Yeah, and that was so much fun that we want to do it again. And I'm so glad we made it happen again because everybody's schedules are so busy and you never know. But we did, and we're here today. So I'm really, really glad. And yeah, I guess since... Hello, Eric. Thanks so much for being here with us. I think you were here with us last year as well, so you might remember shenanigans from last year. So this year, I mean, we already teased it a little bit last time because I think last time we had like an example that I don't know actually, I can't remember exactly in which context they sort of came up, but we had it and we were like, we're gonna explore that next time. So I don't know, do you remember exactly which?
About ImmutableArray.
We had an ImmutableArray somewhere.
So we were thinking about because we promised to talk about ImmutableArray now. We were thinking about what else should we talk about. Well, I guess we could talk 2 hours about we could talk 4 hours about ImmutableArray. So at first we were like, can we talk 2 hours about ImmutableArray? And then we realized that the challenge is to just talk 2 hours about ImmutableArray. So let's see how this goes.
I think that's always the challenge. Yeah.
It is. So maybe let's recreate the pitfall that because as the title of this episode, immutable arrays are built for speed, not comfort. So a bit of a pitfall, a bit of an aesthetic, not aesthetic, but usage correctness thing you have to keep in mind when using immutable arrays.
Usage correct what?
Correctness.
Okay. Is that what? So, okay.
I would hope so.
I'll just buy it.
Because I think there is a category in .NET analyzers that's called correct. Is it called correctness or is it called differently? Let's find out. where are the? No, it's not correctness. Is it reliability? Usage. Okay, no, usage is the correct term. So yeah, so there are a couple of usage pitfalls when it comes to immutable array.
Yeah. Well, I created a little method that gets an immutable array, and then it's just for each it. So as a little bit of a start. And yeah, like for example, well, we can call this method maybe with an array. Well, we need an array as well. Okay, let's create an array as well. Immutable array of int, and call it array. Well, let's just use a trusty collection initializer. What happened here? And okay, perfect. 1, 2, 3. So 1, 2, 2, also good, but let's have 1, 2, 3. All right. I think this is a solid start.
Yeah, this should do
also
1, 2, 3. Yeah, and yeah, we were using immutable array because the Roslyn, the compiler APIs, they pretty much almost everything there is immutable, including the arrays. So yeah, whenever you have a contiguous array, it's not a regular array because that's mutable. You get an immutable array in order to safeguard the contract of Roslyn's immutability. Oops. Stuart is here, and he is mentioning.
Hello.
Correctness is
okay.
a thing. Oh.
Okay, so it tells you a lot about me that I've never heard it.
So today
so
is about correctness. There we go.
Yay! Hi, Stuart. Thanks for joining. Good to have you. We might need your help. Let's see.
Same goes for performance. Oh yes. So today is about correctness and performance, definitely.
Yes. You promised that we'll do some benchmarking already ahead of time. So
yeah, definitely. So we do performance correctness. Yes.
Oh my god. Okay. Intense episode.
Yes. So we had something like this. And then at some point we had a use case where we might not have an array, or was it for a test? I can't quite recall. I think it was a test.
Me neither. Yeah.
Because immutable array, what is an immutable array? It's essentially just a struct. And what you can do with structs, you can say default. Structs can never be null. Struct always has a value, and we passed default. And then, although it is a value type cannot be null. However, we still ran into a null reference exception related to a value type, which is not
magic
what one would expect. And there is
that's really cool. Yeah. Well, no, I mean it's quite powerful. It's like, oh, you think this can never be null? Well, watch me. Okay, but how does this work?
Yes, that's a fair question. So I guess we can. Oops, I just closed everything. No, not closed, but minimized everything. I guess we can do a bit of a not diversion. What does it mean to upstripe?
I know exactly what you mean. Wait, go on a tangent or something?
Yes, which is, I guess, our signature move.
Yeah, that's not a signature move. If you knew, so this is what it's all about. Did you know? 20 years ago in C#.
So let's go a little bit on a tangent here. Let's take a look at what an immutable array is made of. Do you know how to use reflection in order to inspect the fields?
I don't, but Stuart will help me. No, but we can. Okay, so what do we do?
So trying
Yeah.
to guide you here a little bit. So,
Yeah.
well, in order to use reflection,
Yes.
we need a type. We need a type. And how do we get the type of a specific...
With type of.
Yes, exactly.
Okay. Okay. So type is type of what? What do we need as type of?
Immutable array.
Immutable array of int.
And fun fact, we don't... No, not really a fun fact, but more of a fact.
Oops.
We don't need... this is... If you put in a concrete type into the generic, because, well, immutable array, it's actually a generic type, similar to list and pretty much all of the collections. Well, the generic collections.
That is nice.
Well, we can't use T because in the context there is no T. Well, if we actually fill this, I think this is called a constructed type. So the T will be replaced with int.
Oh.
So then we actually get... It's no longer generic, it's now constructed. All the T's are now int. But if we want to take a look at the type itself, the type declaration, without having a... no, it's not concrete type. I forgot the name. Like a I forgot it. But we can also take a look at the generic type definition with reflection. And by that, we just omit... We just omit the type. For a dictionary, how would you do it for a dictionary? Because a dictionary has a generic arity of 2. So it has a T key and a T value. Well, you just do a comma. And this is similar. This is also similar now with C# 14, how the name of works. So if you want to have like the name of dictionary, you just do... You need a comma here because technically there could be a type if we are funny and define our own dictionary type, but only with a single generic arity. Class. Now, in order, if we have like a comma in between, that's generic arity of 2 in metadata or in reflection-based data. This is then a dictionary backtick 2. So this is indeed referring to the system.collections.generic.dictionary. But if we were not having the comma, now in our case, it actually refers to our dictionary with generic arity of 1. So that's dictionary backtick. Oh, typo, but yeah, dictionary backtick 1. Well, this is how it's called in metadata. The name of operator ignores any generic arity, so this will still be just dictionary without any genericness in there. But yeah, so okay, I managed to get on a tangent while going on a tangent.
What is surprise?
Cool. So let's go back to type of the immutable array. And now, do you know how to get all of the fields of this type?
Well, I know, but let's just dot it and see what we get. Maybe. I don't know. So I have assembly qualified name, attributes, base type. Tricky. I get a lot actually.
There's a lot of it. Yeah, so you may want to do some filtering. Maybe search for something like fields.
Okay, fields. Get fields, easy.
Yes. Now this returns this actually returns an array. So yeah, I guess let's enumerate it. And I think there is a feature. Would you mind holding off? Because there is a feature that I don't really use in Rider. And I think I want to give that a try now. Can you?
Go for it.
Let me give that a try, because I think there is something like postfix patterns.
Wow.
So if I do dot for each and then hit tab, oh no, why is it enter?
No.
Yeah, then it returns, then it does this, and I'm using this way too little, and I just was thinking about it.
Yep. Okay, we're gonna use this from now on.
Yeah.
Let's.
And then let's print the fields, but now we will get. Wait a second. We will get empty. Do you know what this is? This is actually a static field.
Uh-huh.
This is not an instance field. This is immutable array.
Yeah.
If we say immutable array of int dot empty. This is essentially the equivalent to if we have an enumerable. Enumerable of int dot empty. Oh, wait a second, that goes like this, my bad. So this is how you can get an empty immutable array. So this is actually the static field, because that's public. So per default, reflection only gets the public members and fields.
Mm-hmm.
Do you know how to get also the private members or the non-public members? Have you used it before?
I don't know. I have not. Sounds illegal though.
Well, there is something called binding flags. If you take a look at the implementation of get fields, per default it uses the default binding flags, which are instance and static members that are public.
Mm-hmm.
So we could take that and say, hey, we only want to get the instance members, be they public or non-public. So that includes internal, protected, all of them.
Mm-hmm.
And when we do that, we no longer get the static field, but we now get all of the instance fields, and we see that immutable array essentially is only made out of an array, as well, like a regular array. The .NET array, so immutable array is just a super thin wrapper, and it's a struct to avoid additional allocations. It's just a super thin wrapper that now only offers methods and indexes that ensure immutability. Because with a regular array, well, we could go into the array, index 1, and replace the value.
Yeah.
With an immutable array, however, we can't. Because the immutable array's indexer only has a getter. It doesn't have a setter.
Mm-hmm.
Well, fun fact is that the array's indexer has no setter either. But still,
come on.
Yes.
What?
Yeah.
But why?
I guess that's a bit of a trivia thing.
Yeah. Okay. So
let's return there.
Nobody
okay,
needs setters anymore.
Now we are inception style. How many layers deep are we in the tangent world now?
I already lost track. we can play some Hans Zimmer and we'll be fine. Wait, where is I need a little thing to spin.
That's the spin?
Yeah, from Inception.
Yes, to check if we're in the real world.
Yeah.
I thought we need a
already
kick
lost
at some
track.
time. Yeah.
Oh. That can be arranged.
Are you kicking me?
Not yet.
Well, we are also on kick. Ooh, is that a sign?
Oh, we are! Oh my goodness.
Okay,
kick.
Now I'm getting a little bit paranoid, but that's a different story.
Why? Because I'm kicking you at some point, potentially.
On kick.
If things go too far.
Yes. Where were we?
Setters.
Arrays indexers don't have a setter either.
Okay.
The thing is, this has always been since C#1.
Yeah.
Well, forever. .NET 1, better to say.
I told you we're going back 20 years. How old is it?
25 or 26. Was it 2002-ish? I have something with 2002 in mind. I think this was the first release, so been a while, yeah.
Okay, .NET 1. They didn't have a setter. They just...
But we can still, maybe let's do let's see, mutable.forEach. Okay, I love this. So just to show, we do an array of 1 to 3, and then we can mutate the middle one without a setter, because what's actually happening is the array's indexer is returning by ref. So when we do this, we actually don't set the element at index 1. We actually return a ref to, so essentially an alias to the item at index 1, and then assign to this item, which has the same effect, but it's technically not an index setter. Because what we can do...
So we just get the address and overwrite whatever is on the address, which is not a setter, but it acts like a setter. So what is a setter? It's exactly the same. How does a setter work then?
No, a setter is essentially a... Let's come to that.
More tangents.
Yes. Because what we can do is actually write ref here. Because the indexer is returning by ref. And now we can literally assign to this ref, and we will now have the same behavior. 193. If I weren't doing the ref, what do you think we will get now as an output?
All right.
Without the ref?
I don't know. Didn't we just have that and it also overrode it?
Not quite, no.
Okay, well then it's probably 1, 2, 3.
It is 1 to 3 indeed. Because, well, we actually return here by ref, but we don't do a ref assignment here. That means we copy.
Oh my goodness.
Int is not a reference type, but a value type. So we get a copy of 2. So we just create an item that has the same value as the 2, but this item and so this variable item and the item in the array at index 1 have nothing in common. They are two different memory locations. I should point the stream. They have two different. That's difficult. Okay, two different memory locations.
Yeah.
That have the same value of 2, but they have nothing in common. So if I change one, the other one remains unchanged. Well, if this was...
if it was a string array?
If this... Yeah, well, strings... well, yes, actually, let's do that. If it was a string array...
This is why we're sort of not good for each other. Like, I think you have a tendency to go on tangents, and I have a tendency to ask questions that lead to tangents.
It would be the same.
What? Wait.
Although, yes, well, string is a reference type.
Yeah.
So we now have at this point in time, item, since it's a reference type, is essentially not pointing to, but is referring the same toString in memory as the index in item 2.
Yeah.
So they're not, item is not referencing this, but they're referencing the both thing in memory. But now here they are still two different, how to say this? They are two different references that in memory point to the same string. With this line, we essentially repoint this item now to 9.
Yeah.
Which leaves the original pointer unchanged.
Okay.
If this was a ref, now we would again have the same behavior.
Because strings are also
with int 192.
Immutable.
Strings are immutable. We can't change the string itself. But what we have now is this string, since it's a ref, is not an independent pointer to the same string 2 in memory, but you can think of a ref as an alias to 2. So if you were writing item equals 9 or immutable array at index 1 equals 9, if you think of it as an alias, it will have the same effect. So again, when we have a ref, we are now mutating, we are now accessing this index at item 2 directly.
Yep.
Kind of dereferenced it. And the item at index 2, the item as index 1 was pointing to string 2. And after this assignment, the item at index 2 is now pointing to string 9 in memory. So we see when we have a ref, we only have a singular. We have this one item, we only have this one reference in memory that we kind of change directly. But if we do non-ref, so it's copy by value, then we have two separate references that don't have anything to do with each other. Those two references may point to the same thing. They may reference the same string, but you can assign a different reference to them individually. But when there is a ref, then it's an alias, and then if you change one thing, you change the other.
Okay. I think I get it.
And you were asking a question, and I said I will come to that in just a second.
Yeah, what is a setter?
Oh, a setter is essentially just a method. If we do we still have the, yes, we still have the, oh yeah, sorry, one more thing. Since we mentioned .NET 7, I think, I always forget, I think it was somewhere in the C# 7.x, I'm not sure if it's C# 1, C# 7.0, 1, 2, or 3, somewhere in there, we got ref locals. So we could now actually write this ref. We couldn't do it before. Mm-hmm. And which means that line 11 and 12 is equivalent to line 14. Because whether we store the reference in a separate local variable and then mutate the reference is the same thing as we do in line 14, just everything in one go. Because this is returning by ref, and then we just assign to this ref. So those two blocks are essentially equivalent. But if it's not ref, now it's something different. Because here we are accessing the ref because the array's indexer is returning by ref. But here now we create a copy. And now we have two separate references that point to the same thing, but have nothing in common. And okay, now to go back to the question, what is a getter? We can not only get fields, we can also get methods. Well, we can get all of the members. We can also only get the methods. And an indexer is essentially just a combination of a get and or a set method. And we should see, we see also something. This is actually how a ref looks like. It's the %. It's like in C, it's a reference. It's not quite a pointer, but it's a reference. But we see we get, this is essentially the indexer's getter, get item. And there will also be an indexer set item. I guess a little bit below, if we can find it. Get length. This is, for example, the because properties are essentially what in C# is a property is in an L code. There are no properties; they're just methods. And somewhere we should have the set. If we find it, can you search set underscore item? Oh, I was, now I'm confusing myself. I thought there was a set item. Well, those are the set items from IDist because an immutable array is also implementing some collections.
Yeah.
I'm not sure where. I'm not sure what doing wrong here. Oh, no, wait a second. No, I'm not certain. I was expecting now a set as well, because an indexer is essentially just a, if we do a class and have an indexer. Wait a second, indexer is this int index. This is how you would do an, wait a second, how do we want to write an indexer? Now I'm embarrassing myself. Is it not like so? Oh yeah, we need to return something. Int get set. And of course we need to do something. The getter will just return 1 and the setter will just be empty. Doesn't really matter for the logic. Why is this not valid? Oh, because we have blocks and they like so. Ah, cool. Okay. I haven't written index in a while. So what I would now expect, if we inspect C, we should get the indexer's get and set method, I hope. There is the get item, and there is the set item.
Set item, easy.
So we see the set item is, well, we now have int32 twice because let's use a different type. Let's say we have, it's a string, the properties of type string, and we have an int-based indexer. So we now see in IL code, those are just methods. That C# is understanding and essentially allowing it to access it with this property syntax. So you don't really call, you technically could call this get underscore item via reflection, but C# says, okay, I interpret this as properties. That's like the pattern, yeah. Or well, it's not really a language pattern, it's more of an IL pattern.
Oh. Okay.
Because C# is turning this into IL, and the other way around, if you consume a library, then C# is allowing, or only allowing, to get this, or use these as properties, unless for extension members. This is what Stuart showed us in the C# 14 stream. When you have an extension property, because there is no property in IL, you also get these methods, and you can actually call this get underscore item and set underscore item in C# as well.
Okay.
I think actually, I have never tried. Can we? I don't think so. If we have an instance of C, can we say C dot get underscore item?
Yeah.
I hope not, because I would have
think
been
you need
wrong.
to.
Cannot explicitly. Oh, there we go. Cannot explicitly call operator or accessor.
Huh?
So
why not?
We see this
unsafe there or something.
We see these things exists, but C# just doesn't allow it. For extension properties, it does, but just not for regular properties. Yeah, because you should use the indexer.
Okay, fine. I can do that.
It's a C# rule. You could, however, with reflection. What you can do is call it via reflection. So you could get the method. Now I'm not sure. I think it's exactly like this. You get the get item method.
Yeah.
Make sure this is well, we don't need these binding flags. It's an instance public member. Let's actually give that a try. Let's actually give that a try. Now it gets crazy. Let's, you know what? Let's try something.
What?
Okay.
Yeah.
But it's read only. Now I'm not sure if this works, but this is totally unscripted. Let's see if this works. We actually have this example here.
Yeah.
And this still fails dramatically.
Okay.
Because the underlying, there is still something null. Maybe let's come back to that. Let's put a pin in it. Access get item direct. No, wait a second. That's the indexer. No, this wouldn't work. What I was thinking about. So what I was thinking about wouldn't work. So let's have let's have our string indexer. So let's, I'll just make it public for simplicity. Public with only string array that has 1, 2, and 3. And I still don't, this is how we do it. We return a string. Come on. Okay. And the getter would access this array by index. And the setter would set the value that we set to this array. Okay, cool. So we have a simple indexer. Let's create an instance of this class, and we should get, or we can access the array directly for each. Just to check it, we should get 1, 2, 3.
Yes.
And what we could, of course, do is access this array directly and say index 1 now is 9, which now should be 193. But we should also be able to instance this, access this via reflection. So let's get the type. And then get the method, the actual set item method, what this indexer is turned into, which has binding flags. This is an instance public. Well, I guess we wouldn't need those binding flags because they are the default, but just to be explicit. This method, because this is nullable if the method is not found, should not be null. Because if it's null, that means it's not found, because we could say something like this and this member doesn't exist. So we need to be precise in the name. And then we should be able to invoke this setter where we pass in an object, which is the instance that we want to mutate, or the instance of which we want to invoke this method on.
Mm-hmm.
If it was a static property that we will be accessing, we don't have an instance because it's static. If it's an instance member, which it is, we need to pass in the instance that we want to invoke, and now the value. And in our case, it would be, oh, that's an array. In our case, this would be 9. And now we haven't done this in a while, but this should now have the same behavior, but via reflection. No, target invocation, parameter count mismatch.
Oh.
Because
what?
We also, because we invoke, we saw this in reflection, the set item method.
Yep.
It returns void, and it actually takes 2 arguments.
Yep.
One is the value, and one is the index. But I forgot now which is which. The order. So let's just print this method info. There it is. Okay, the first one is the index. The second one is the value that we want to set. And yeah, well, we want to set index 1 to the value
1.
9.
Oh,
and this should now be the equivalent of invoking the indexer with index 1 and setting it to 9. Oops.
Yep.
Should be the equivalent. And if we run this now, let's see if it actually is. And there we go. So nice. Yes, we can access these methods, but not per default with C#. But it's still there. We can do it via reflection.
Awesome.
And Stuart is mentioning that in C# 15, because we currently only have extension extension methods and properties, but we will get extension indexes too.
Nice.
So I suppose we could then in the future have a extensions extension block. I'm now probably messing up the syntax. I don't have a preview installed yet, so something like then essentially just moving it in here, right? This may be just a syntax for no. Wait, we need a class we need a receiver because it's an instance property. So this should then work with, yeah, I think this should then just work with C# 15.
Nice.
Maybe let's copy this. And when, for our episode in November.
In November, we are like, oh, do you remember on April 1st, we said this would work. Well, I love that. Yes, do it. We won't forget. We'll remember. I can already see us in November. It's like, wasn't there something?
Yeah.
Okay, but actually we were talking about immutable arrays, and you were telling me about this reference, right? Where you can kind of set something that doesn't have a setter. And I thought this was how setters works, but it doesn't. It's not how they work because they have these methods underneath.
Because the
so
array,
they don't do any reference magic.
Because an array,
is that right?
Yeah, because an array.
Yeah.
Get type dot get members. Let's get all of the members of an array. I've never done this. I hope we can see something in here.
Me neither.
We should see kind of confirm what I claimed, that there is no. Oh wow, those are all the. Oh, there is a set. Okay.
No, but today you're doing it. You're doing it wrong. It's April Fool's Day, so what you should do is just like make a statement, make like a claim, and be like, "That's the truth," and you can note this down. You can this is what it is, and if it's not, you can be like, "April Fools." Just kidding.
Yes.
You believed me. This is all planned.
Damn it.
Next time.
Yeah, I could have. I'm not wondering. It actually doesn't show the indexer at all, does it? Well, this just get and set methods, but those are not those indexers with get underscore. There is an address. This would be length, long length, and rank properties. There is set value. Okay, so maybe it doesn't even have an indexer. Okay. So does this mean that array doesn't even have an indexer, and it's just what C# kind of emulates?
What? How?
Yeah, maybe the compiler just rewrites the code. So if we, oh wow, we're not talking about it. Okay, this is a tangent. If we do something like this and set it to hello, it should be a string. I mean, this will fail because it's empty, but what does AL code say? If I could read it.
I can, hello is there somewhere. That's what I can see. Load string hello. That's what this one says.
Replaces the array element. Okay, so yeah, there is some. It doesn't even call like some. There is some IL code instructions that work with array. So there is no indexer even. But if we
that's so weird.
But if we use the indexer in C#, it does return by ref. We have proven that actually, so that's not fooling. But okay, there is no indexer at all. Like there is no spoon. Cool.
Oh my goodness, there is no spoon. We're just kidding. Okay, cool. Lovely.
No indexer. Okay, cool. Take away. What are we talking about? Immutable array. Yes. And yes. So we learned...
What was the title of the episode again? Immutable arrays.
learned that an immutable array essentially is only an array as a field.
Yeah.
And only having public and wrapping this with only public members that do not allow mutation, so that it is indeed immutable. But under the hood, it's just an array, which is mutable.
An array is mutable.
Yes.
Yeah.
And why
is
this causing a null reference exception? There's another component. When we have a struct, struct, let's say we give it again, making it public. We're now doing public fields, but let's not worry about them. Let's say we have a string called text.
April Fools.
When we April Fools, which is, what is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 characters. Well, whenever we have initializers, we also need to declare a parameterless constructor.
Yep.
And if we now create a new instance of this value type and would be printing the length of this value, well, we would be calling the constructor and we would expect 12. Because April Fools has a length of 12. What if I write default here? Damn it, why are I smart and giving it away?
Oh, lovely.
So what
I guess
we...
in a class, we would still have the same, right? Because in a class, the constructor is always constructoring.
Well, with a class... What is
wrong?
With a class actually can be null. So instance.
Oh. Yeah, okay, a class can be null, but
instance
the field
now is null.
Text is not null. And so if we initialize
yes. So if we were calling this parameterless constructor, then yes, this field would never be null because it's read only and we initialize it during construction. Unless we provide so that's cool, but we are not in a class. No. What if this is a struct? Well, if it's a struct and we still call like this constructor, well, we call the constructor, and in our case it will be April Fools. So that's also cool.
But default does not call the constructor, and therefore we don't know, like this text April Fools never gets initialized, right?
Exactly.
Right?
So reference types, fields of reference type in a struct can always be null. So technically, the compiler doesn't warn about this. That's a bit of a... That's intended. Otherwise, that's intended. That's a design decision, because you would get so much nullable warnings all over the place. But to be correct, one could write an analyzer. Maybe we will.
One could write
someday
on the next episode.
Analyzer to do analyzer struct ref type field null. So we should actually, to be correct, reference types in a struct can always be null when you do default, because this constructor isn't called, and not even this initializer, because this initializer is part of the constructor. So this is never called. And what happens when the struct itself, the instance itself, since it's a struct, can never be null, but its fields can always be null. That means we here return null, and here run into a null reference exception.
Yeah, because the length of null is death and destruction.
Exactly. Right? And this is what's happening here, because when we do default, the underlying array will be null, and immutable arrays are built for speed, not comfort. So we kind of need to do this check ourselves. I mean, what they could do is because what is a for each? A for each is essentially getting an enumerator and then turning this into a while enumerator dot move next is true, then get the current item. So the calling get enumerator will already internally throw. This is where we run into the null reference exception. And because the underlying array went default is null.
I just wanted to say, if you came to see any of our talks where we talk about language patterns, we always get the question, when do I need this? Well, in this scenario, maybe potentially
for debugging
to know what's
purposes,
going on.
Yeah.
For debugging purposes.
Exactly.
Cool.
And yes, so I mean, what the team could do is essentially say, hey, if the underlying array of this struct of this immutable array instance is null, then return an empty enumerator. That move next will always return false, something like that. But that would mean that essentially every method, and we saw earlier, immutable array has a lot of methods, would need to do this null check. And immutable array is built for speed, then we would always have this null check. And that's a design decision to not do that.
Yeah.
Because immutable array should be as thin as a wrapper around array.
Yeah.
And we need to keep in mind that it's a struct and the underlying array is a reference type, which may be null. So if we don't know, if we are like a library and we don't know who might be calling us, so we don't have control to ensure that a default instance is not passed, then we may run into this null reference exception. And I guess what we could do, depends on the purpose of the library, is do something like there was a check array dot is empty.
Yeah.
Which will always fail if it's null. Because what the is empty check is doing, it's just checking if the underlying length array is 0. But if it's null, it doesn't do the null check either. The only two members that do the null check for performance purposes is the is default check, which literally, checks if this underlying array is null, which happens to be the case when it's a default instance, or is default or empty, which does two things, checks if it's null or empty, just what we saw. So it's combining the is default and is empty. Cool. So what we could do is check, is this default? And if it is, this is something that we might want to do in our library, throw a new argument exception. Instance must not be default, something like that, with a name of the array. If I'm not mixing these up, message parameter name, yes. So I guess we could do something like this. So we don't run into a null reference exception that we would not expect when we pass structs around, but actually get now an argument exception. So this is something that we might want to do in our library, because immutable array is built for speed, not for comfort.
Nice. Yeah, but it makes sense. You don't need to be comfortable all the time. Right?
Well,
yeah, look who's talking. Like me, you know, oh, when's my next spa day?
Now I have a bit of a question for you.
Oh my goodness, yes.
What about,
since
we were talking about patterns, what about collection initializers? 1, 2, 3.
Yeah.
What will happen? Actually, why did I remove the check? If array is default, throw new argument exception. Yeah, we should add something. Well, there we go. Name of array. No defaults allowed. Okay. What would you imagine happens now? Do you want to be the compiler and do a bit of a lowering there?
Well,
because we talked about this some while ago. This is a pattern.
Yes.
Because maybe
is
this
a
helps
pattern.
understanding what will happen.
Because I guess we call add on array for each item in the initializer. So this is kind of what's happening underneath the hood. Ooh, and I get a warning. So does that help me in any way, maybe, to answer your question? I don't know. Who knows? So this is actually what, oh, you can't see my, I forgot that you can't see my mouse. But yes, so kind of, this underneath the hood looks like that. This is what the compiler makes of it. So I know that this method.
Oops.
Oh.
I will copy this, comment it out. So what will happen is actually now this, or like this. This is not what's going to happen. Yes.
Yeah. So we create a new array and we add to it, and then
there's 2 problems.
Why? I didn't do much. How can I have created 2 problems with 3 lines?
Well, the collection initializer already has 2 problems.
Oh, okay. So it was there before. Good.
Yes.
But what was your question? What happens now when we call?
What do you think will happen if we run this? Yeah.
Okay. Well, if array is default, we throw an argument exception. Array is not default.
Yeah.
Right. So we're good. Then we for each it, and then
is array not default?
It's not. No, it's not, because we do new. We don't do default.
Yes, but immutable array. Well, I didn't tell you. Immutable array. I'm now emulating, like I'm now the .NET team. It's a public struct. Is it even read only? I think. Immutable array of T. We implement some interfaces, and we have. One constructor. Oops. Okay, let's public. We have one constructor. Actually, oops, it's not public, it's internal, which takes an T array and then assigns the array. Array. So like the array field. It's not compiling, so we get a lot of equals array.
Okay.
This is essentially, I'm not sure if it is precisely, but essentially what the only constructor that we have. That means we do not explicitly have a default constructor. But this still works. So this is essentially the same as this, and writing default is essentially the same, because if we had a accessible parameterless constructor,
we would be
this
fine.
one would be called, but there isn't. So, and if there isn't, then new parameterless on an array is always possible.
No.
And then it's essentially, no, not essentially, but then it's the equivalent as if we were writing default. So it is. Or, well, there could be, maybe actually this could be the code, there could be a public parameterless constructor, but it's not setting the array to anything. It's not doing like array equals empty array or something. It's, if there was, which it isn't, but even if there was, it would still do nothing. So the underlying field is still null and still equivalent as if it was default.
Okay.
So what will happen if we run it?
Argument exception.
Not quite.
Why?
There is no argument exceptions. What's the exception that we'll get when the underlying field is?
Oh, null reference exception, but we check for default.
Oh yeah, no, we don't even come to our method.
Oh.
We already fail at the first add.
Great.
Because the first add
we'll
just do an is empty check. Well, it's a bit unfair. I studied this code quite a lot. So it just does an is empty check, and is empty doesn't do a null check, so we will run here into a null reference exception.
Okay, cool.
That means collection initializers
are doomed.
Are not supported. Collection initializer will always fail.
Again, why didn't I know this before the talk? Because then I could have answered this question. When do you need this? And it's like, well, when you're trying to initialize an immutable array.
Immutable array will always fail, yeah.
There you go. I have an answer now.
There's a second problem though.
Oh.
Let's say we initialize it to something, because a collection initializer will work. Collection initializers will work because they will.
Collection expression.
Sorry, you're right. Yes, collection expressions will work. And in this case, then the underlying array will be assigned to a new array of int. This is not how you write it. Int array with value 1, 2, and 3. So this is essentially what will happen. Not directly, because there is a lot of span stuff going on, but essentially, in the most efficient way, this is what we will get. So if we had 1, 2, 3, now I just initialize it to empty. If we run this, we get nothing.
Oh, wow. Oh, wow, because it's a reference. And so we are doing no?
No. What is this type called?
Which one? Sorry. Immutable array?
The type that we are talking about. Immutable array. If we
it's immutable.
Exactly.
We cannot mutate it.
This is not a list. If it was a list, yes, but it's not a list. It's an immutable array.
Of course.
It still has add and remove methods, and some remove all and something.
But they're just for fun. They're just for April Fools. They're like, try me.
Well, no, they will return a new instance.
Okay.
They will each return a new instance. And now we have 3 separate immutable arrays, where the first array in this case is empty. Now we add one element. That means we get a new array, or we now get a new immutable array, where the underlying array has only as a length of 1 with the item 1. And wait a second, let's actually do here. Now we have this length 1 immutable array, of which we remove, well, we should remove 1, of which we remove 1 again. So instance 2 now is again an empty immutable array.
Okay.
Not default, but empty. So on instance 1 and instance 2, we could actually, this will not run into an argument exception, but it is empty, because it's not default, but it's empty. And if we use instance 1, we will only have the 1. And if we do add, let's say an adder 2, add returns a new instance, So we actually under the hood create a lot of new instances of immutable array. And with that, a lot of instances of underlying arrays that the immutable array is wrapping around.
Yeah.
So if we were to construct an immutable array by using add methods, this is super inefficient. I guess it's time for benchmarking.
Finally.
Let's go to I just want to copy paste the package name to not run into any benchmark.net spoofing. I'm getting a bit paranoid these days.
Well, today is the day to get paranoid.
Oh yeah. Documentation install. Where do we go? Oh, there we go. Add package. Actually, let's even go package reference, and let's add item group benchmark.net. So we get the benchmark. We should restore first, right? Then we have everything available. Benchmark.net runner, and we run our benchomat. Class benchomat. We also want memory, a memory diagnoser. We only do a short job because we're live on stream. and do a benchmark where we, let's say, now we want to create an immutable array. Well, create with add. Well, and if we use a collection expression, that's as fast as it gets. But maybe we don't know ahead of time what the elements will be. Maybe we combine from two enumerables or something, where we could end up essentially doing something like new immutable array dot add. Let's say we add three items. Add 1, which returns a new immutable array with a length of 1. Add 2, which returns a new immutable array with now a length of 2 because it contains 1 and 2. And add 3, which now returns a immutable array with length of 3. Let's return that. And we essentially now created 3 different arrays.
Mm-hmm.
What this returns, it will be null, it will be default. Then we create an array with 1 length. We create an array with 2 length, where we copy this 1 over and add a 2. And then we create an array of length of 3, where we copy the 1 and the 2 over and add the 3. So we created 2 intermediate arrays that we immediately discard and have created some garbage, essentially. And if this was, I don't know, a longer for each group, this would be super inefficient. Is not visible. Yes, it is not indeed. And after a quick run, we should see that, actually, what should we see?
Yeah, what are we expecting?
What are we expecting?
Slowness.
Okay, let's do some math in the meantime. Oh, it is super fast. Something went wrong. There are not any results. No workload results were obtained. Exception has been thrown. Oh, yeah, my bad. This is null.
Oh.
Yeah, I made a mistake. Null reference exception. What we could do is using the generic one. We could use the empty field, the static field that we saw at the beginning, which creates a new immutable array with length of 0. Now it's default. Now it's no longer default, but well has a length of 0, and now we don't run into the null reference exception. Yeah, I was essentially just now mimicking what a collection initializer was doing again, but just manually. This should now. So, damn it, I always forget, what is the overhead of a reference type? I think that's like 24 bytes. And then we have an array. Array also has a bit of an overhead, but I always, not an overhead, but the length, because you have the item and the length. I always forget, but something in that ballpark. Then we have an integer that's 4 bytes. So we have 4 bytes here. Then we have 8 bytes here, and then we have 12 bytes here because it's 3 elements. So that's 42. So I don't know, something about 50, 60-ish. Okay, it's even more. Well, we could actually find out the exact numbers. If we say create 1, let's return an int array with length of 1. New. Let's create 2 as well and 3 as well. So this should essentially give us a bit of a baseline, and then it should add up.
And how? Okay.
Well, there is still also the instance of immutable array. So this should be. Let's see if this kind of adds up at least to some degree. What we would expect. Okay, this might now take a while.
That's okay. I have a question. And then the new, you have a blue line underneath the new. Is that the analyzer that you're showing me before?
Yes. So I have a plugin that's called the Heap Allocation Viewer.
Yeah, that's really cool.
The Heap Allocation Viewer always gives me a little blue underline if there is something allocated on the heap. And really cool. Arrays are reference types, so they are heap allocated.
Yeah, that's really fun.
And now the math should somewhat add up.
Okay, let's see.
So we have, oh, wait a second, that's also.
Oh my goodness.
Okay, there's also some rounding going on, I suppose, or some, not that, some, what is that called? Some padding, I think. So we have 40 plus 32 plus 32. Does this amount to 104? 20, live math.
Yes, it does.
This would be 49. Oh, yes, it does. Yes, it does. Okay, so this is essentially what we are doing. We create an array with length of 1, 2, and 3, but discard these again. So we produced 46 bytes of waste just to get to the final 3-length array.
Yeah.
Because of that, there is something called a builder, the immutable array builder. And this is how you properly build an immutable array. So you would create an immutable array. This is a nested type, builder type. Immutable array also has there is a static immutable array that is non-generic, which has some helper methods to either like create an empty array, to create an array with just one item, or an immutable array with one item, to create an immutable array with 2 items. So there are some helpers to create an array from a read-only span, to turn a read-only span into a mutable array. So there is a bunch of helper methods, and one of them is to create a builder. And the immutable array builder is super similar, not quite the same, but super similar as a list. It is still managing an array under the hood, but this one is mutable. This one can grow and shrink, of which we then can create an immutable array. So here we could now do the adds, 1, 2, 3, and then return an immutable array by saying to immutable. And what this is then doing, it's actually again creating a new array from there. Because an immutable array can be reused. What we could technically do is we only return the second, is do this. So we can reuse a builder.
Yeah.
And when you say to immutable, that still keeps those elements in the builder, but the underlying array is still copied to ensure that if we say to immutable twice, those are still independent immutable arrays, so that this immutable guarantee, is actually guaranteed. If it wasn't, if we would say that this to immutable would actually copy this internal, not actually copy, but kind of move this internal array managed by the immutable array builder into an immutable array instance, well, what we could do, then we actually have a kind of so if the immutable array that we create here is referencing the same array as the builder is, we could afterwards say build.remove or change is 1. And if this first and this builder would reference the very same array, now it would be violating the immutable contract here. Does this make sense?
I think so. Builders are like a help.
Go ahead. Sorry.
It's like a helper kind of thing to avoid.
Yes, and which still ensures that every instance created has its own copy. It has its own copy of the array. Nobody else has a copy. So first and second will have, although they are based off the same builder with item 1, 2, 3. There will be two separate instances of arrays that don't have anything to do with each other, so this immutability is guaranteed.
Lovely.
But if we were only to create one, well, actually, I'm not sure if this actually will be create with builder, will be more efficient as this one, because what we are doing is when we create a new builder and we start with the builder, well, it's super similar to a list. When we have a list and we add an item, we then have a capacity of 4 of that list. And we can add 4 items. After the 4th, when we start exceeding the capacity, we then double the size. So we have a capacity of 8 and then can add 4 more elements. If we add the 9th, we get a capacity of 16 and so forth. And the immutable array is very much the same behavior. So it has, if we exceed the capacity, we double the length, well, we double the size of this essentially buffer that we use to create this array. And then when we actually call to immutable, it calls to array, what essentially now does create a new array of the current count, not capacity. Because if it was just copying this array over with the same capacity, it could be that because our immutable array builder starts with 4 elements, but if we only fill 3 elements and would now create an immutable array of the entire array, the immutable array will suddenly have a length of 4, but it should have a length of 3. So we create for the immutable array a new array that only has 1, 2, and 3. So it is actually correct. And yeah, that's all ensured by this immutable array builder. So this is why I'm not sure if this actually would be, for this case with just few elements, would be more efficient. Well, I think immutable builder also has a overload where we can set an initial capacity directly. Because in this case, we have this doubling thing. So here we would create an array of length of 4.
Yeah, and
then by 2 immutable, we create another length of 4. So we may be actually allocating more than with these. But if we were expanding this sample with, let's say, 100 adds, at some point, it will be more efficient to use the builder. Because when we have add, we always create a new array. When we use a builder, we have a more efficient doubling kind of growing algorithm. And we could also give a hint. If we know we're going to add 100 items, we say 100, and then we don't have any additional growing going on and are more efficient.
Lovely.
And produce less garbage. But there is an optimization. What is it? Array builder. So this is, because I mentioned immutable array builder is similar to list.
Yeah.
But it's particular for building immutable arrays. So there is one optimization, and that's surfaces in 2 methods. When we hit 2 immutable, under the hood, we create a dedicated new array. Now there is 2 methods. There is move to immutable and drain to immutable.
Yeah.
I will show this in an actual example so we can see this. So let's do a bit of let's always print the capacity and the length of our immutable, of the builder. So the builder has a capacity of whatever and a count, so the current length. When we add, every time we add, when we only do it 3 times, we should see the capacity not increase, but the count increase every time. And when we exceed the 4th, then we should see that it's growing under the hood. Let's first kind of settle the stage here. And I was wrong. If this was a list, if this was a list, we see it actually starts by 4. So initially, I'm now changing to a list of t. So initially, the list starts with a capacity of 0, length of 0. We add
That's
1,
weird.
then we get the 4, and we can add 4 times until we exceed the capacity. Then we get the doubling going on.
Yeah.
Actually, and I didn't know, the immutable array builder starts with 8, not with 4.
Yeah,
Default.
that's really funny.
We could still, I guess we could still emulate the same behavior by setting an initial capacity of 4. Now we should get the same behavior. So we have initial capacity of 4, and then have the same doubling to 8.
But it's also interesting that with list we start with 0, like with nothing. Like I also thought for some reason that we start with 4.
No, we don't.
Add.
But that's again an optimization, because maybe you create a new list and never even add an item to it.
Yeah. Then
so we start with an empty array. Because if we would just for the fun of it allocate an array of 4 but never adding to it, then it would be a waste already.
Yeah. But also with immutable array we don't have that either. Right? We start immediately with 8.
Well, that's the immutable array. No, we don't. So did it?
Yeah.
Oh, it does. Now I know what you mean.
Oh my goodness, you like.
Now I know. Okay.
I like literally when he questioned me like that, I like questioned everything. I was like,
no,
did I?
No. I was just wrong.
I cannot trust my eyes.
That's also because we say to builder and a new builder, it starts with 8. Okay.
Yeah.
Well, I suppose creating an immutable. I can imagine because sometimes, I don't know, if for testing, well, I can imagine, this is not what I'm guessing that the design decision is. For testing, if you want to create an empty list, you just say new list. But then already kind of assuming and pre-allocating with a 4 is maybe a little bit too hasty and we may produce some garbage. But a immutable array builder is meant to add stuff to it. So creating an immutable array builder and never calling add is kind of totally weird. Because a real builder is, then if you don't add, then just create a new immutable array, or well, that would be default, or say immutable array and then empty. So I think that's the design decision. But that's actually learned. So we would need to exceed 8 items to get the double growing going on.
Yay!
And maybe it's 8 because maybe it really starts using the builder, maybe it really starts kind of amortizing when we have this capacity. When we start with 4, because what we saw earlier, no, we didn't show it, but I mentioned that it may not be, when we only have like 3 adds or something, it may not amortize in efficiency. Maybe 8 is like the number where it starts being then more efficient. So there may be some heuristics why there is an 8 for the immutable array builder and not for the list.
I can totally imagine that, yeah.
Right, okay, so we add a little, but what if we don't, actually, let's stay with 8, yes. No, let's stay with 9. Okay, so if we now create an immutable array of that builder to array, to immutable, excuse me. Well, we need to create a new copy of that array because the builder's capacity here, we're at a point where the builder's capacity is 16. So the array that the builder has is of length 16, but we only added 9 elements. So the length is 9. So we need to create a new array with the length of 9 to have a correct immutable array. Now there is 2 methods. We could use move and drain to immutable. Because what if the capacity actually is matching? In this case, we have a capacity of 8 and a length of 8, or a count. now we could, what I mentioned earlier, we actually could, since this kind of matches, we could move. Oh, sorry, that's actually the move I wanted to show. We could actually move the array of the builder into the array so that we don't need to create a new array. Because when we say to immutable, we now have a builder with an array of length, and creating a new array will here create a new array for the immutable array that also has length of 8. So we end up with having allocated 2 arrays with length 8. But what if we kind of know that we're going to have a certain length or capacity? Maybe we even set the capacity to something to be super explicit. And we know we don't want to reuse the builder later on. So we're going to discard the builder. We technically could move the array that the builder has into the immutable array so that we don't allocate 2 arrays with length of 8, but only a singular one. And this is what move to immutable array does. If we take a look at the implementation, well, it first does a check if the capacity equals the count. And then it copies, this is the reference to the array. And then it calls this internal constructor, which is setting the array directly without copying it. And in between, this builder is kind of emptied. The builder's array is set to an empty array, and the count is set to 0. So we kind of reset the builder.
Oh, okay. So we can still reuse the builder.
We can still reuse it, but after that, the builder's capacity is now 0. Let's actually see if this is true. Yeah, we go. So maybe we also do a console write line if here create. And we see that after that.
Okay. So but because actually we don't start at 0, but once we move to immutable, that's when we start with a capacity of 0. That's really interesting, actually. It's funny. I wonder what the decision there was.
I believe because when you use, maybe because if you create a builder and never add to it, that's kind of weird. But maybe you create a builder only to create one array and then, or to create one immutable array and then stop using the builder and let it be garbage collected. It could be premature to just create another length 8 array, because in our case, it would be wasteful. We would create for the builder another array of 8. So we now have again allocated 2 8-size arrays, but we wouldn't be using the builder later on, discard it, and then essentially a prematurely allocated garbage that we not use.
Okay, fair enough.
I think that's the design decision. And yeah, now we only create, if we were wanting this to benchmarks, we would only create one array with length of 8, which is now moved into this immutable array. But yeah, the builder must be cleared, because if the builder wouldn't be cleared, if the builder would still have those elements in it, the builder would be again referencing the same, would now be literally referencing the same array that the immutable array is referencing under the hood. And now we could kind of start violating this immutable contract and change items again. Okay. So we need to clear, this is why the builder then under the hood is cleared, so that only the immutable array, kind of, this is what the name move also infers. It's moving ownership into the immutable array. And there should be only one ownership. If we would have 2 components having ownership of the same array, and one is mutable, the other one is not, the immutable component could violate the immutability of the immutable one. Do you know what I mean?
Yeah, I do know what you mean, yeah. That's pretty cool. What does strain do?
Yes, because what if we are in this scenario? If we now add 9 elements, the capacity of the array, so the length of the underlying array of the builder would have a length of 16, but we would only have added 9 elements. And immutable array only is an array. It doesn't have like additional length, because a list actually has 2 fields. No, it has 3 fields, the version, but let's forget about the version for now. A field has the array, but also a current count, because a list allows this growing. And maybe we start with 4. When we do one add, this underlying array of a list has a length of 4, but we only added 1 element. And when we for each, we should only iterate through 1 element. And the other 3 elements that we still have over are just a buffer that could be used later on, because if we add now a second element, we don't need to allocate a new array. So this is an optimization of the list. Immutable array doesn't have this optimization. Every time we create a new immutable array, we create a copy, and every time we get a new array. But the list has this growing under the hood, similar to the builder of the immutable array. And if we were now to move this array with a length of 16, but essentially only added 9 elements to it, this immutable array would have a length of 16 and not 9. And this is why there is a check. If the capacity does not match the count, invalid operation exception, because we would not create an array with a length of 9 as expected, but an array with a length of 16. And this is why drain exists. Drain does the right thing. If the capacity of the builder matches the count of elements we have added, then it does a move. If it does not match, then it does a copy. A copy and clear. And move and clear. It always clears the builder. And we can take a look at the implementation. This is literally what it does. If the length does not match, we call toArray, which under the hood is now creating a new array with the current count and copying the elements over that we have in this builder array, and then clearing it. But if the elements match, we don't create a copy here, but we use the original array and just move it into the array. So essentially what move does. So if capacity and count is equal, we do a move. So we do not allocate an additional array. If they do not match, we need to allocate a new array with the expected length. So drain kind of does the most efficient thing it can do.
Yeah. Nice.
And that is essentially, apart from the default capacity, the difference between list and immutable array builder, because the immutable array builder is meant to create an immutable array from, and the list is meant to be consumed directly. Now we talked a lot about ownership. Do you want to write some unsafe code?
Yeah. Oh my goodness, definitely.
Okay. We still end up doing some shenanigans. Maybe let's use here an example. Because so the immutable array builder ensures that the ownership model is correct, and we can't violate the immutability promise.
Or can we?
With unsafe code, yes, we can. Well, with currently not unsafe, but soon to be unsafe code.
Yeah.
So let's create an array, immutable array of int. And we say builder.drain to immutable, which we should use, or which we should use if we don't use the builder afterwards. If you want to create an array 1 with 8 elements, and one with 9 elements. Now we shouldn't use drain, because drain resets the builder, and now this one is only 1 length. But if we expect this to be 9, then we need to do 2 immutable to get the behavior we expect. But yeah, so for our example, we can use drain because we stop using the builder afterwards. And well, array doesn't have the indexer of array, doesn't have a setter. We can't mutate it. It would kind of be bad if we could mutate it, because then it's not an immutable array. Would you like to write some unsafe code? This is actually not necessarily. This is currently not necessary, but I still want to add the unsafe here just to indicate that we are now doing some memory shenanigans. This is soon to be, what this may soon to be unsafe code. Would you like to take a look at a type called Marshall?
Yeah, I remember we had the memory Marshall at some point.
We had the memory Marshall, and we used that for span. Yes.
Yeah. Marshall.
Or maybe find memory. There is memory Marshall as well. Yeah.
Yeah.
Whenever you have some Marshall, yeah, that's.
I can see immutable collections Marshall.
Exactly. There is a lot of Marshalls. There's immutable collections Marshalls. There's a collections Marshalls, which is unsafe stuff for generic collections like list. There's memory Marshalls for like spans and such. And there is immutable collections Marshalls for immutable collections, such as immutable array. Let's see what methods are on there.
Yeah. I don't know. As array?
Mm-hmm. What they call as array?
My array in there, maybe.
The immutable array, yes. Maybe I just rename it into immutable to make this more apparent. And
but
what does immutable array return?
It returns an array, right?
Mm-hmm. And that's that's a good old array. That's well, do you know why it's nullable?
Yeah.
I'm being a bit of an annoying.
No, I know it. No, it's okay. It is of course nullable because default would be null.
Very good.
We did that before. We did that an hour ago. I do have like a weak brain sometimes.
Well, then you can keep way more context, and your model can keep more context than mine does.
There you go.
Exactly. If we were saying immutable default, this would be null. In our case, it won't be. Yeah, correct.
And then I can like maybe index into it and overwrite it. Can I do that? Like here, and then is, I don't know, 9.
Yeah. And now let's say this is just some, I call this consumer, and I would be passing this array to a consumer. Now this is some, okay, we still do something. Happy.
Yeah.
I'll put this unsafe here. It's currently not necessary, but I just want to state that this is, whenever we have something with Marshall going on, this is unsafe. And there was a possible null reference. Well, yeah, we could do a null check, but never mind. Static.
We're already unsafe. Like, what's the worst that can happen? No checks, nothing, no testing. Test in production. Ship it.
I should use the ship it for each pattern. Yes, not pattern. How's it called? Postfix completion, something like that. And consume. Well, from my perspective, I for each through an immutable array once, I for each through a mutable array twice. I would expect that those are both, well, immutable, and is 1 through 8 consistently. And we have 1 through 8, and then you shenanigan index 0 into 9.
Yay!
So you can break the immutable contract because, yeah, what as array is doing, literally, just returning this private array, or is it internal? I think it's internal. The internal array of the immutable array directly. And now you have access to the mutable field that the immutable array should be shielding from.
Yeah. I love it. That's pretty cool.
And
this makes me happy.
This also works the other way around.
What? You can
This also works the other way around.
My code? Definitely not.
Oh, no.
Not
but
today.
this is how you extract the immutable array.
Yeah.
You could also
and immutable
directly
connection marshal can also, I saw this actually when I dotted onto it. Let me go back. Okay, I'll use my keyboard. Whee! I also found as immutable array.
Mm-hmm.
So this is what you mean by other way around. Yeah.
Exactly. Maybe let's do, sorry, you have a different context. Could you revert that?
Oh, yeah. Okay.
And I'll just copy another method here. Let's call this produce. I just do the signature. You do the implementation. I give you an array.
Yeah.
And you return me an immutable array.
Yep. I'm getting, this is a bit tricky. Okay. As immutable array, I'll take your array, and then here I'll have, so immutable array, and this is going to be an immutable array of int.
In our case, yeah.
And I will return that.
Mm-hmm. Yeah, this is not the other way around. So if we now consume that, or if we now would be, let's say we have an array, int array, oops, not quite. What does it say? 1, 2, 3, 4, 5, 6, 7, 8. And I would want, well, an immutable array from it. Maybe I call this produce method. I see produce takes an array and returns me an immutable array. Haha, I would assume immutable array indeed is immutable. But yeah, since this is now the opposite, this is just calling this internal constructor that directly just sets the array. So this is also what like move to immutable in the builder calls and such. This is not publicly available because we could mess with the immutability promise. But with this, well, this is actually exposing this constructor with in a type that has Marshall in it. So this will be unsafe. And yeah, I would assume here is an immutable array. So, well, maybe I can do stuff with it afterwards. Maybe setting this to, what do you say, index 0 to 9. And although, well, I have an immutable array that I iterate through twice. Yeah. Again, the second iteration now has not 1 as the first element, but 9.
9.
Because now this array, this immutable array has a reference to this array, which is mutable. And again, potentially violating the immutability contract.
Nice. There's also a third option. There's as memory.
I never used this. Let's explore it. Memory. Would you mind? I've never used this before. Would you mind doing it? Let's explore this.
Yeah. I've never used this. Oops. As memory of int probably.
Yeah, I guess we don't need that necessarily, but yeah, shouldn't matter. It takes that one takes an immutable array builder actually. Dot builder. I never used this before. Let's explore this. So we could use, well, we still have our builder, right? Maybe instead of having our immutable array, let's use the builder. Well, because an immutable array builder is also implementing iList and iRead-only list, so it is IEnumerable, so we can for each it. And let's see what we can do. Just iterating it twice should give us one through. Oh, wait a second.
Yeah,
that doesn't work. I'm just removing this for now. 1 through 8 twice. Yeah.
Okay.
If we were now to call on this builder, this memory method that under the hood uses, the memory, I would assume it calls as memory on the builder and it returns a new memory. Okay, and I think memory, the type memory, is very similar to span.
Cool.
But it's not, it is larger because a span only has 2 fields. It has a reference to the first element of contiguous memory and the length of the memory. But it is a ref struct. So this cannot be boxed. This is always on the stack. Memory is a regular struct. This may be boxed. This may live on the stack, but it has more fields. It has a reference to the contiguous memory. It has a start and an end. No, it has a start and a length, essentially.
Length, yeah.
And yeah, and it's not a read-only memory, it's a memory. So we could, with that, now essentially also access the builder and say, hey, on element 1, we now set element 1 of the builder to 9. This does not work. Ooh, memory doesn't have an indexer.
Ha!
So what we can do is say span. Oh, no, not span, but access the span and then index that. So of that builder, we could set that. But that builder is mutable.
Yeah.
And so there isn't really, from that, we didn't really do anything unsafe yet.
Yeah.
But what could happen is, because this is kind of, now what this memory is doing, it has, because we saw a memory consists of an object, an index, and a length. So what this memory will be doing is it will be pointing to the same array that the builder has. Well, the builder's array currently, or in our case, oops, whoa! Maybe let's remove 1.
Yeah.
Actually, let's remove 4. So we only have 4. The array of the builder currently has a length of 8, because we saw that. But we only added 4 elements to it. So what this memory will be doing is pointing to the same array with an index of 0 and a length of 4. So if we were to write index 5 here, we should get out of range, unless I'm mistaken. Yes, index out of range. But we can still just mutate the first element. So the first element, index 0. So we first have 0 through 4, 1 through 4, and then 9, 2, 3, 4. But an immutable array builder is mutable, so we could just do that directly as well. Let's say index 1 to 99. So we now have 9, 99, 3, 4. So we haven't really done anything unsafe here just yet.
Yeah.
So, but the unsafety now, you said previous, like, haven't you?
Yeah.
Can you remember what you wanted to say? Because you may be onto it.
Oh my goodness! Well, because we have a length and if for example, and if the length is like longer than what we have in the immutable array, then we could access memory that's not ours.
Well, this is actually
like
not the case because this is checked. This is checked. If we were to index element 100, we actually get an index out of range exception. So,
no, but if we set the length of this memory of int array, to something that's longer.
I'm not sure. Could you write that, because I'm not sure what you mean.
Because memory has a field length, right?
No? Yes, but we can't change that.
Oh, okay, never mind.
No, we can't change that. The unsafety here comes in. What if we add? Actually, I will now set the capacity of this array to 4. So we can save 4 elements without having any regrowth going on.
Mm-hmm.
And we saw the current behavior is first we get 1 through 4, and then, 1 to 4, and then 9 to 3. Because we muted the builder here. But what if in the meantime, we would add another element to the builder in between? What happens now? This may be a little bit of a mind check. I want to say the nasty word. Can you imagine what the result now will be?
Not quite.
It's not going to be 1, 2, 3, 4 and 9, 2, 3, 4. It's going to be 1, 2, 3, 4, 1, 2, 3, 4. Oh, is it?
Because you're adding one. You're not replacing.
Oh, wait a second. That's actually. Wait a second. Yeah. Now I'm confusing myself. No, actually, yes, that's true. So it's going to be 1, 2, 3, 4, 1, 2, 3, 4.
Oh my God.
Oh, actually, 1, 2, 3, 4, 5. That's right. That's right. Let's add a 5th element. Let's make the example shorter. Let's say we have a capacity of 2. We add 2 elements. Now I'm confusing myself. And here we add a 3rd.
Yeah.
And we do this in between. So we first iterate through the builder.
Yeah.
Then we call this memory method, and then we iterate through it again. And in this method, we get the current builder, which at this time has a capacity and a length of 2. Then we add to it. And then we set from this memory that we cached earlier, let's call this memory, index 0 to 9. Without the add, we get 1, 2, 9, 2.
Yeah.
1, 2, 9, 2. With the add, we get 1, 2, 1, 2, 3, not 9, 2, 3. Can you imagine why?
Yeah. Okay, so like I'm up until line 41. I think I'm good. I'm still figuring out 42. But because we have a capacity of 2, then we add a 3rd element, so we get a new array with a capacity of 4.
With a capacity of 4, so we now have 3 elements in a capacity of 4. Yes.
And then. Okay, and then we change from the memory array with a capacity of 2. That's where we change index 1 to 9.
Yes, exactly. Exactly. So the previous builder.
Yeah, I get it.
Here with references, let's say this array of 2. Here we exceed capacity of 2, so we create an element of 4, and the builder is now pointing to this, but the memory is still pointing to the 1, because this memory is disjoint for the original builder. There is no, they just originally point to the same thing, but now this builder repoints to the other thing, and the memory that we extracted doesn't recognize that.
Yeah.
And this is where the kind of unsafety comes in, because through this growth of the array of the builder, it may now suddenly start being a different array. And now this memory is no longer referencing the array that we intended it to be. And this
Yeah.
is why it's also unsafe. And this is the very same that we have with list. When we have a list of int, there is not immutable collections marshal, but collections marshal, where we can say as span, pass in the list, and then we get this list as a span. But when we start adding in between, let's say we have a capacity of 1, and we add element 1, and then we add element 2. Now we have this doubling, same with the builder, we have this doubling growing algorithms going on, having a new array, and the span is still referring to the old one. And this is where the unsafety comes in, yeah.
Nice. Cool.
I didn't know as memory, cool. Since we mentioned unsafe a lot, it's currently not needed, but I think it will be needed in the future. When we go to github.net/Roslyn, there is the good old that also Stuart is showing us every year. If we go to documentation and the language feature status, there is the unsafe evolution. And part of that unsafe evolution, if we go to the github.net runtime repository, which also contains the base class library, there is an issue about, let's search unsafe. That's the issue. Annotated libraries requires unsafe attribute. So .NET 11 will have this requires unsafe attribute. Because currently, well, when you do unsafe, it's only related to pointers. So when we have like an int pointer, for that we need to be in an unsafe context. But it's only the thing with pointers. Well, yes, they're unsafe because we can do some pointer arithmetic and then point to memory that we don't own. But with this unsafe evolution, there is now this new requires unsafe attribute that you can annotate methods with, and I think also properties and constructors that require the caller to be in an unsafe context, to kind of also tell the reviewer when you look at code, there is the unsafe keyword, there may be some memory shenanigans going on. And well, they will put this attribute at everything that is unsafe, in the unsafe class, many items on the Marshall class. So what we just did may have this attribute in the future. And everything that has this attribute in the future then requires to be in an unsafe context. So when we upgrade to .NET 11 and C# 15, if this feature gets completed by then, we may need to be adding unsafe here. And I will just be copying these examples because we could also have a callback there when we do the session with Stuart in November.
Nice.
So we have some callbacks going on.
Yeah. We're already prepping.
Yeah, yes. And then I think there is one thing left. I think then we check our item list. Oh, we have a lot of usings. Let's only go immutable. Okay. What I showed you earlier is that an array allows, or the array's indexer, which doesn't really exist, but C# style, returns by reference, and we can directly mutate elements in a collection or in an array. And yeah, because this is actually returning by, or has by ref semantics, I guess that's more correct to say. But with immutable array, well, immutable array is immutable, so we can't set it. But the index of a immutable array is not returning by ref, it's returning by value. But what if, so there's a copy going on. But what if we don't have ints, but we have some large struct that has many fields. Let's see, 3, 4, 6, 7, 8, 9. So it now has 10 ints. Let's actually make them longs. So this struct now has a size of 80 bytes. Because a long, that's an int64, that's 8 bytes. And we have 10 fields, so this struct is 80 bytes in size. And when we have copying going on, we would copy here 80 bytes. Mm-hmm. And if we do this a lot, and in a hot path, we may want to optimize this a little. So because we copy here 80 bytes, if this was an array, we could actually write ref here, get a reference to it, and the reference is whatever the processor architecture is. So it would be 4 bytes on a 32-bit machine, or on a 64-bit process, it would be 8 bytes, which is just a 1/10 of the size, so significantly smaller. We are in the bytes area, sub-kilobytes, but just to draw out this example. Do you think there is a way to do the same to get the by ref semantics on immutable array as well?
Yes, there is.
Would you mind exploring this?
No, I don't actually know what it is.
Well, let's search it. If there is something that has ref semantics on the immutable array.
Okay. Ref, like you up here? No.
Oh, well, let's not do it in the constructor, but in the line afterwards.
Yes.
Maybe no. Let's do a new line. I just keep this as an example. So we want to essentially this only works for an array. But can we emulate the same behavior for an immutable array?
Well, there's item ref.
Yeah.
Oops. Yes. There it is.
And that's exactly it. Well, because the thing is, arrays, they always returned by ref, even before C# had the by ref return feature.
Yeah.
But immutable array existed before the C# version, before this item ref was introduced. So the indexer returns by value. So you can't really change the by refness. I think that's a breaking change. So they added later on a new method, item ref, which is essentially, it's very similar to indexer. It takes it's not quite an indexer, but it's indexing into, we see, this is what it does. It indexes into an array, just as the regular indexer would be doing. Well, still ignoring null, so we could have null refs exception if we didn't check for default, but returns it by ref.
Yeah.
Well, to be exact, by ref read only. And well, if we now index into this, we actually now can get the same semantics as we have here. We can now get a reference to our large struct with this by ref. And well, it's not ref, it's ref read only. Because if it was ref, what we could do then is essentially reassign it, what we saw earlier, what we can do with array. And now we would be exchanging the element at index 1. And we could now it's kind of, and we would break the immutability contract yet again. Therefore, it's returning by ref read only. And ref read only disallows reassignments so that we keep the immutable contract. but we now have the same semantics of like a by ref return from array. This is now also an 8-byte reference that we get, and not a 80-byte copy. And I think this is, oh, no, there's one more thing. There's always one more thing.
There's always one more thing.
Because there's always link.
Yes, there is.
Would you like to
No,
do some?
but yes, of course.
Yes. It was a question.
A rhetorical question.
Rhetorical question meant as a command.
Okay, let's do it.
Would you mind only printing items larger than
oh my goodness,
larger than 5?
So there is select and then there is the other one.
There's select and there is where.
Where?
What is select doing?
Don't know. Select.
What is where doing?
Where is filtering?
Where's filtering? What is select?
Grab. I don't know.
It's a transform. So
how is it transforming if you're selecting something? I don't.
Well, because that's the link. That's the names that link. That's the names that SQL chose.
Oh.
And then the link is well, we need to operate on the array.
What?
I think in other link.
Oh yeah.
We need to operate on the array because that's just.
Because we're just iterating. Oops. Yes. Cool. Fabulous. Okay. Wait. Okay. So let's do array dot. That was not array. Let's try this again. Array. Wait. What am I doing again? All right. What do we need? We cannot.
All
we can do where.
All items that are.
Yeah.
Greater than 5, or something. Was less than 5, something like that, or exactly 5. Doesn't matter. But some filtering.
Yes. Great. Yes. Where X?
I'll help you. I do some defensification. So this is just an integer.
Ah. And now
it starts completing.
Telling you.
Why does it do? Does it listen? Why does it show the 5? Ryder, do you listen? That's troubling.
But I forgot. Wait, we said greater.
Yeah, something. It doesn't matter the exact. Just that we get some filtering going on.
Okay, that's my filtering.
Let's use greater than 5. Yeah. We can.
Yep.
Yeah. No. Go ahead.
And now we need to pass this to the for each, right?
Yeah.
So names are tough. Great. Something. Filtered is okay. Ta-da! Easy peasy, lemon squeezy.
Sweet. Let's give that a try, and we indeed get 629. Splendid. Now, link. It's an IEnumerable. No, wait a second. I gave it away. Stefan. I wanted to have an array there first. Okay. I gave it away. I'm so schlecht. Right. Those link extension methods.
Yeah.
They take, well, we just gave a talk about the patterns of C#, and you mentioned that, for each, we don't need IEnumerable necessarily, but for link heavily relies on IEnumerable.
Yeah.
So essentially so there is some implicit conversion going on. An array implicitly implements or is convertible to an IEnumerable. So what's kind of going on? I think the compiler is optimizing this, but from a more strict point of view, what's kind of happening is we convert this to an enumerable and then act on the IEnumerable somewhat in the terms, because the where takes an IEnumerable. What about immutable array? Immutable array is a struct. Immutable array does implement interfaces like immutable lists, immutable array, list, equatable.
Oh, yeah.
And in particular, I-read-only list and I-list, which eventually then, well, I-list is a I-collection, which is an IEnumerable. So eventually implements the IEnumerable interface. So this conversion is possible. But you mentioned the plugin earlier. Do you see something in there? I'm zooming in.
Boxing, or like at least some.
Correct.
Yeah.
We have here a heap allocation, and correctly we have boxing. Because you have boxing going on when you convert a struct, a value type, into the interface that it implements. You have boxing. I think this is with .NET 10, 11, and plus, this is no longer always true. If you keep this in a local function and there's no asynchrony, then the just-in-time compiler is optimizing this, and you may not have this. Yeah, I don't know. There's so much optimization now going on, but just from a source perspective, aesthetically analyzed, we get a boxing allocation here. If I'm now removing this explicit conversion here and doing it implicitly, there is no, this plugin doesn't, this heap allocation viewer doesn't mention the heap allocation here.
But it does in a for each.
Excuse me?
It does in a for each?
It does in the for each. Oh, yes, because we allocate an enumerator.
Okay.
And
since we have a funny laugh.
Since we have IEnumerable here.
Yeah.
And when you have IEnumerable and call get enumerator, you will allocate. Yes.
Yeah. Okay.
We will then see when we use a list. This won't happen, but we will come to that. But we don't have a heap allocation here. This is because the .NET team added overloads to link for immutable array, because immutable arrays are built for speed. And if we wouldn't have particular overloads, my F12 doesn't work on me. There we go. If we wouldn't have link overloads for immutable array, we would have boxing. In order to avoid the boxing, there is in the system link namespace immutable array extensions, which are not all, but the most prevalent link methods. Select many, where, and so on. Any to avoid the immutable to avoid the boxing allocation by taking the immutable array. Well, calling this method, because if it's default, it should throw an exception immediately. And then just access this underlying array, which is a reference type already, not a value type. And then we essentially got the same conversion that we saw earlier. And then we can use the actual IEnumerable implementation and avoid the boxing. So this is the actual implementation of where. And this is how we can avoid boxing allocations by providing immutable array overloads for the link methods.
Awesome.
And well, I mentioned list. If we turn this into a list and don't have IEnumerable at all, well, we should actually call this list. There is no boxing allocation here.
Well,
can you imagine why? There is no IEnumerable going on here.
Yeah.
List has a get enumerator method. Let's see if we can find it. There we go. The get enumerator method, which returns an enumerator that is struct-based.
Ha! Cool.
So list got an optimization there. If we enumerate a list, we don't, well, we still allocate an enumerator, but it's a struct-based enumerator, so we avoid heap allocations for the enumerator.
Yeah, but the collection expression has an allocation.
Yes, because under the hood there will be, sooner or later, there must be an array allocated, because the list uses an array under the hood. So sooner or later there must be an array, which is always heap allocated. Yeah. Which is in this case, when it's in a class heap allocated, it's not it's not always heap allocated anymore, because there is I think in cases like this, if you have a method, I'm not sure if this is .NET 10 or 11, but let's say we create an array with a length of 3, and then assign some things to it. 1, 2, 3, and then return like array at index 2 and return an integer. Yeah, this is totally constructed, but something like this with modern, I'm not sure at which version, but I think the JIT, the just-in-time compiler, now is it the runtime? Not sure. Sees this pattern, understands that this array is never leaking out. It's not returned. It's only used within this method. So this technically could be stack allocated. And I think this is then stack allocated and returning then essentially free here. There might even be some more optimization going on. Maybe the compiler even sees through that and just returns free directly, because it's kind of sees through the patterns. The JIT compiler is getting super powerful these days. But yeah, arrays are not necessarily always heap allocated, but in this case, when it's in a list, which is a reference type, this has to end up on the heap, because the list is a class which is very likely on the heap. And yeah, that's also a bit of enumerable and how we have some link to avoid boxing allocations.
Yeah.
And we got some feedback from Eucalyptus Q. Use slice.
Ha! Yes, I like slice.
Actually not sure if ImmutableArray supports slicing. It does.
It does?
And it returns, well, yeah, it returns a new immutable array. But that means it creates a new array under the hood in order to fulfill the immutability contract. So there may be some copying or creation of new arrays going on. Oh, unless unless the slice that we create has the same size as the original immutable array, then it doesn't create a new array. But if we're creating a view into it, then for immutable array, this will cause a new allocation. So if we slice, actually let's use the slicing syntax. If we cut off the first and the last element, this will under the hood allocate a new array. So we cut off the first and the last element with slicing, but we essentially here have an immutable array backed by an array with a length of 9. And in here, we create a new immutable array that is backed by an array with a length of 7. But yeah, slicing is supported through the, since we have a length, or not, ranges are supported because we have a length. We have the slice method and what was the third component? An indexer, yes.
No.
So we have an indexer, and with these 3 components, the range is supported. Yeah. Oh yeah, with span slices, we could avoid that. But I'm not sure. can we convert an array to a span? Oh, but this must be a read-only span, otherwise the immutability contract would be violated.
Yeah.
So, this is how we could avoid allocations. That's correct. I didn't know there is. Well, I never used this actually. So if we were to use a span, now here is no allocation going on. That's right, because this span is now a span that essentially has a reference to this element and a length of 7, pointing to the same array under the hood and not creating a new array. Let's see if this is true. Yeah, because we use this backing array as an input for the read-only span. And it's still read-only, so we can't do any mutations, and the immutability contract is still preserved, but without allocating anything new, being most efficient. Cool. I never did that before.
Awesome. Yeah, and it's a really cool plugin as well with the allocations, by the way.
The heap allocation viewer, yeah.
Yeah, I'm also gonna remember that.
Oh yeah. There's also C-Link, right? I never used C-Link, and C-Link is like link but for spans.
Oh,
because with link, with the regular link, that's enumerables, and you create new enumerables or new enumerators. I mean, link these days is super heavily optimized. There's a lot of optimizations going on, but sooner or later there will be some allocations here and there. And I think C-Link is kind of, it's like link for spans to avoid. I'm not sure if it's most allocation free or always, but I guess as allocation, if it's not 100% allocation free, then it's as allocation free as it can be.
Yeah.
I never used it actually. Perhaps we should at some point. And speaking of NuGet, so immutable array is I think it's since .NET. Is it always since .NET Core or since .NET Core 2 or 3? It's like part of the base class library. In earlier versions, like in .NET Standard 2.0 or in .NET Framework, it's not included. For those, you would need the NuGet package, System.collections on immutable. And System.collections on immutable not only contains the immutable array, it also contains other immutable collections, such as immutable list.
Cool.
Or immutable dictionary. And like an immutable dictionary that has like the same semantics as a immutable array. So when we add, we actually create a new instance of an immutable dictionary. But unlike immutable array, because we saw with immutable array, whenever we add, we create a new immutable array instance that has a new array under the hood. The implementation of immutable list, immutable dictionary, and other immutable collections, they use some, some trees. There is a particular tree structure that they use so that there is not always creating an entire new copy of everything. So there is some references, some reusing. I'm not sure if I'm explaining this right. I may not. But because it's been a while since I looked into it last. What I think now is going on here, not entirely certain. Well, A is empty. B has essentially a node that contains this key value pair 1, 2. Well, I don't think this is super true, but something in that term. And then we get C, which not has 2 entire new nodes, which consists of these 2, but I think reuses the previous node, which it can because of the immutable guarantee. So there is some internal optimizations going on. The implementation of immutable dictionary, immutable list, they are not so straightforward. A-B trees or something like that. I always forget. So there is, I wouldn't quite understand the implementation, I suppose. mutation result. Yeah, there is a lot of stuff going on. So this is highly optimized, which is actually a fun fact that immutable list and immutable array, they are kind of optimized for adding. So adding is as fast as possible, but iterating through them may not, because it's not consecutive. An immutable array is a little bit different, because an immutable array is essentially just backed by an array, and the array is always consecutive in memory. So iterating through this is super fast, because it's just going from one memory address to the next until we hit the length.
Yeah.
We have immutable dictionary. I think this is not contiguous array. There may be various nodes across the memory. So it may be jumping around in memory locations. So for eaching is a bit more expensive, but adding is not. which is kind of weird the first time I read this, that immutable list and immutable dictionary are optimized for mutation. Well, you don't optimize, they're immutable, but the internal tree structure, there is a lot of reusing going on to optimize this behavior. But iterating may not be as fast as it is with a regular list or a regular dictionary.
Okay, but oh yeah, no, that makes sense. That's really funny. That's interesting.
So there is quite a difference between immutable array and other immutable collections. From a behavioral perspective, no, not from behavioral perspective, but like from performance perspectives. But from a behavioral perspective, from an observable behavior, they all have this immutable guarantee. And when you add, you get a new instance that is in itself, no, not necessarily in itself, but which is observably immutable.
Awesome.
Well, now I'm taking a look at our list if we covered everything. Oh, this has been a lot. Okay, so we covered that immutable array is just a thin layer over an array, ensuring it's immutable. We talked about arrays, we talked about structs, we talked about the immutable array builder, we talked about immutable collections marshal, we talked about link, we did some benchmarking of performance, and we talked about by ref returns. And this all got started because we, for each an immutable array, which was default, running into a null reference exception. And immutable arrays are not built for comfort, they are built for speed.
They are indeed. Yeah. We do go on tangents, but yeah, I guess, and we also did some shenanigans. So we did play some tricks on April 1st, which is the most important thing, which is what we set out to do. Well, yeah, I guess I hope you also learned a thing or two and didn't come to this episode and knew everything.
No, I didn't. I mean, we designed this episode and we didn't know everything.
Exactly. That's always the plan. We always want to have fun. We always want to learn something new. And that's the whole point of the stream for us. And it's always such a pleasure to have you all live with us, and spending the evening with us and learning with us and exploring. The language, the frameworks, everything. So thank you so much. When will... Oh, for Ostern. Ooh, almost. Yes. Cannot wait. I'm actually really excited.
Easter weekend is coming up. Yeah.
It is.
Sorry, I was interrupting you.
No, that's it. I just wanted to know when if we already have something scheduled for next time, because this is like, we sort of broke out of our usual sort of format. We will be back with with Inspector Roslyn next time, and
but we will be back on Tuesday again.
Yes.
This time for real. Well, I think last time we also announced Tuesday, but then we thought, May 1st of April. Let's break our streak and let's go April Fools.
Exactly. Oh my goodness! We should have posted that. We should have done this like, just kidding. We'll have it on a different day.
No, that was a missed opportunity.
Next year.
We will do next. I'll make a post. Prepare fake announcement. So we're back in 13 days.
Yeah.
And we will return to Inspector Roslyn, since we got now some safe, non-remote code executable vulnerable functionality going on, and we want to pack this into a .NET tool for the world to use.
Exactly. That's the plan. So hopefully see many of you there.
There is Eucalyptus Q. Hi. And there is, I think Eric has, I'm not sure, maybe a fun fact or an April Fool's fact. So this will be German. Let's do some. Would you mind translating it? I'm not sure.
I should translate it. Okay, so breaking news. So the castle was shrank it's 14% smaller now, and scientists suspect that it was washed with too hot temperatures. So I'm so bad. I should never be a live translator for anything. So if anybody was considering hiring me, I guess don't. No, but it's Sorry.
Well, as opposed to the live translation you can pull off is more like C# to IL code.
Oh yeah, I can pull that up. Well, only with my IDE. I can't do it from the top of my mind. Oh my goodness. Yeah. Anyway, there's a really cool Easter market at Schloss Schönbrunn. And apparently it also gets smaller each year because of inflation.
What's an Easter? No. I didn't know there was an Easter market.
Yes,
only know Christkindlmarkt.
Easter market. I know, but the tourists love it, and therefore we've extended it because we used to have a Christmas market there, and Christmas markets were only open until Christmas, and then they were like, "But tourists are still here, so let's extend it until I think January or something, but then it's Sylvester market. And then they were like, well, tourists are still here. So let's have an Easter market as well. And but it is fun. It gets you outside and I don't know, socializing.
I didn't know. Cool. So I'm not only learning about C#, I'm also learning about Vienna in the city that I live. Okay, I have really no idea about anything.
Well, that's why we've got the stream to learn.
Cool.
All right. Well, thanks everybody. I hope you have a lovely evening. Don't wash your castles in too high temperatures. And hopefully see you next time.
We are out of trivia today. We will reload for next episode, and for which we will be back.